Hey guys, this is John Michael Hans. I am a product manager and strategic planner at Intel for our data center NVMe SSDs. I also co-chair the NVMe Express marketing work group and the SNIA SSD special interest group. Today I'm going to talk about monitoring the health of NVMe SSDs. This is a follow-up on a topic we did a recent webcast on NVMe Express on this topic that kind of stemmed from a blog post I wrote on the topic, which came from a lot of questions we got from reviewers on how SSDs fail, how are NVMe SSDs different, and what tools does NVMe have to kind of monitor the health and smart information on drives in real time to help kind of diagnose and monitor NVMe SSDs. So without further ado, I'm going to go walk you guys through some of the interesting things that I think that I see of monitoring the health of NVMe SSDs just from experience. I used to run a validation team at Intel, so obviously I know a lot of the failure mechanisms of SSDs in general. Two, I've helped kind of work and refine and define a lot of the features in NVMe today based off lots of customer feedback, based off all the partners that are part of NVMe Express, kind of contributing to the overall specification as far as trying to accomplish these goals. So the first thing is really about how SSDs fail. So one of the things, this is very important for monitoring the health of SSDs because the increased prevalence, obviously, is where to look for as far as what the likely candidate of a failure is. And if you think about things where most people think SSD failures happen, from endurance or hardware failures, but actually, if you look at this, this is a very, very small percentage of actual failures. For one, endurance, you can monitor it with smart. Well, I'll talk a little bit about it when I show the smart logs, but you have something called percent used in NVMe, which is basically the gas gauge that shows what percentage of the endurance you used. And you also have available spares and reserve spares as part of the standard NVMe smart log where you can monitor endurance. You can also project endurance in real time as far as being able to project and model what the endurance of the drive is going to look like over the 5 year life of the drive based off what the workload looks like. And it's very easy to model. I wrote the model at intel.com/endurance, based off some Python scripts that basically do this, basically monitoring the write amplification and projecting the endurance. But basically, in a lot of years of enterprise drives, even with 1 and 3 drive writes per day, class drives being the mainstream drives today, endurance failures are not very common. Just because one, they're understood very well, and two, most customers just um, are not using that much endurance. And we'll talk a little bit of that when I look at some case studies. The other thing is hardware failures. So um, in the long life cycle, so enterprise and data center NVMe SSDs take a long time to get to market. So generally it's a year plus life cycle, and in that there's quality and reliability tests, there's validation, there's hardware screening, there's uh, you know SSD controller power on. I mean, all this stuff happens, and a lot of the hardware issues get weeded out. Not to say that they can't exist, but things like capacitor failures or resistor failures or ASIC failures uh, just aren't that common. Now, media failures. Now, the actual as you look into increasing prevalence now, most enterprise drives are designed to actually withstand media failures. So most of the enterprise drives today, have something like an onboard XOR or a RAID engine, or some vendors call it fail in place. But basically, uh, enterprise SSDs are able to withstand failures. So not only just specific blocks or page failures, but also entire die failures. So typically, this is not a very common failure mode, although sometimes there's a lot of NAND or something or bad firmware that causes more media failures than is normal. And so it's not to say that it can't happen, but it is more rare than what is the number one cause of SSD failures is firmware issues. And one is just because NVMe and all SSD firmware is extremely complex, moving data around, doing garbage collection, monitoring the logical to physical mapping of the SSDs, and firmware in just SSD firmware has become really, really complex, and almost all the majority of failures we see, over 50% are actually just some sort of firmware issue. Now, in this case, it's interesting because most of the time there's nothing actually wrong with the drive, and upon a graceful reset, and we'll talk a little bit about some of the features in NVMe coming to help with this, you can kind of bring the drive back to life. But we're going to walk through kind of how to monitor the health of SSDs to figure out, okay, if you have a drive failure or suspected failure, how do you figure out where it is? And so we'll talk about some stuff like over temperature, incompatibility performance. If a drive is not enumerating or not coming up on the PCIe bus, what do you do? How do you figure that out? So there's a couple case studies that I talked through in the webcast. If you were to go start from scratch, wanted to learn about SSD reliability, which I mentioned is really important if you want to understand how to monitor the health. These are the papers I'd suggest reading. So this first one is this reliability of solid state drives based on NAND flash memory. That was written by a bunch of my colleagues at Intel, many of whom actually pioneered the reliability methods, endurance methods, JEDEC tests for how you actually monitor and demonstrate the reliability of SSDs, endurance, and quality. And then the other paper is this one from FAST last year from NetApp and University of Toronto about a study of SSD reliability in large-scale enterprise deployments. But that's actually using I can't remember. It was like millions of drives out in the field that NetApp had from their customers, and they have their telemetry data back from the field, which they have smart data. Now this study was not done with NVMe SSDs because it was basically using the drives from the last like 6 years, and most of the drives in the study were SAS. But there's some really interesting stuff from the study. One about correlation of drive size and failure rates, and again that goes to the firmware issues about firmware being more complex. It goes into difference between TLC and MLC and different type of 1 in 3 drive writes a day, if there's any correlation between that kind of failure. But the most interesting thing I saw out of the study was one is that SSDs don't fail very often. In the study, their average failure rate was way below the actual 2 million hour MTBF, which corresponds to 0.44% AFR. And then the other thing was the rated life. Percentage used. The most customers are only using a very fraction, like 1 to 5% of the total SSD endurance, which is why I mentioned endurance, even though it's thought of one of these major issues with SSDs. It's just not very common. And then the other one of my old colleagues at Intel, Brendan Watt, who's now a architect for SSDs at Microsoft in the Azure Storage Group, he presented at FMS last year about this topic, basically on how SSDs fail and what can we start to do predictive analytics and machine learning to basically be able to prevent and monitor these things in real time. And so I'm going to talk a little bit about what Microsoft has done to help in a few slides, but NVMe's got a ton of features for helping this basic health monitoring. So the most important one is a smart log page. We're going to talk about that, but that's kind of your main health dashboard for the drive. If basically, if you see somebody suspects that there's a drive failure, again, in Linux or Windows or anything, there can be all kinds of information, like all kinds of bad things that can happen at the application, at the file system, at anywhere in the stack. Basically, if you want to figure out if things are drive issues, Smart Log is a place to go. The most important thing it has is something called a critical warning bit. And now this bit, if you go look into the NVMe SSD spec, you can go in here, and if you go into the NVMe spec, and again, just download the latest one, there's a git log page command. And in the git log page command, if you go down here, there's smart health information. You can just click on it and it will get you the table. This is how to learn about the smart, but basically this is where you need to go to learn about what smart information tells you. Now, and if you go into Linux, and I'll show you an example, the commands will tell you what all this stuff means, and it'll actually parse through the information. But the most important thing in the smart is actually this critical warning bit, which is basically if this bit is set to anything that's non-zero, there's a problem with the drive. And that's the easiest thing to check. If you just do the smart log and this critical warning is not zero, then there's something wrong with the drive. And this can basically, the sub bits can tell you where the types of failure is, whether it's a temperature, a media error, or whatever. The rest of the smart log I'm going to talk through, but there's stuff like composite temperature, which is the temperature, and most of the applications actually convert that to degrees C instead of Kelvin. Percent used, that's the endurance that I mentioned. Available spare and available spare threshold, those are monitoring endurance as well. Data units read and written. This basically, you can see how much data has been written to the drive. But through all this smart attributes, you can really tell what's going on with the drive. And so I only have 30 minutes today, so you just go download the latest NVMe spec. It's open source. Basically, it's available for free on nvmeexpress.org without having to sign up. That's the most important thing. Now, in that other log page, there's something called an error log page, which again makes sense, is for monitoring errors. So when an error happens, it gets logged on the error log page with the queue and other information about where the error happened, and that can help people debug, what's happening, uh, on the NVMe SSD. The other thing is called persistent event logs. This is something new in NVMe 1.4, but it's basically a human readable and timestamped log of events. So the way I describe this to people it's like the black box. And I'm going to go over all these features in more detail in a few slides, so don't worry. But basically, persistent event log can help log when things happen. And again, so when you're an operating system or user wants to go back and say, hey, a drive failed. What happened leading up to that event? They can go figure out, oh, did I update firmware? Did I format the drive first? Did it have power failure? What happened to the drive? And then the most important thing I mentioned, as firmware issues are the number one cause of SSD failures, something called telemetry allows device manufacturers to basically dump a log when there's an error, and then somebody in the field can dump this telemetry log, and then they can use that. There's some telemetry data that can be used for health monitoring, but the majority of the purposes of telemetry log are basically to collect internal logs upon a failure, give that back to the SSD vendor, and then the SSD vendor can go fix those problems, root cause the problems, update the firmware, and fix the bugs. And so again, I stated this in the webcast. If you want to monitor the health of NVMe SSDs and you want to prevent failures, the number one thing you can do is update your firmware, because firmware is the number one cause of failures, and most of the vendors are spending a lot of time and effort, and validation, and quality, and development in fixing the firmware and making it better. And then, part of this whole NVMe Express operating system, the way it supports it is this asynchronous event support. So basically, when things happen, the drive can notify the host of events. And this can be used in different operating systems to basically trigger things like dmessage in Linux or an event log in Windows. But asynchronous events can happen to let the operating system know when things go wrong. The device self-test is one of the things we'll talk a little bit about too, which is basically an offline diagnostic test. Many of the use cases are just like in factory integration or testing, when somebody takes the drive out of a box and they put it into a new system, or if they're repurposing a drive for another system, they'd like to run a short test to make sure the drive is functioning correctly. So the device self-test can go do that. It can do an offline diagnostic test that runs a smart check, it runs the media check, it runs the DRAM check and capacitors and all that stuff. So and then, of course, end-to-end data protection. This isn't about monitoring. It's more about protecting from data. And that's kind of outside the scope of today's discussion. But NVMe has lots of stuff to prevent errors, not just monitoring. So I mentioned the log page. Boy, I wish I had time to go through all these today as part of this presentation, but I don't. You can go to download the NVMe spec to look through all these. The ones I'm going to spend a lot of time on are the error logs, the smart log, and those are the two. The persistent event log I'll talk a little bit about. There's a lot of other stuff going on that are useful, like the LBA status information for rebuild assist and other things, but and the sanitize log for after you sanitize. But those aren't for general monitoring health. The smart log is basically the number one place to start. So here is a picture of the output of me running NVMe CLI on a desktop. Just the command is very easy. It's just sudo nvme smartlog /dev/nvme whatever. You can put the namespace attribute in there as well if you want to run as a per namespace. But as you can see, you dump the smart log out, and you can have all the information that is exactly one-to-one matched for exactly these what's in the smart definition here in the git log page, smart health information here in the NVMe spec. It dumps it out, and then what NVMe CLI or other things like smartctl in Linux or other applications can actually parse this information. So going through it, this critical warning bit, you can see here 0 is good. That means the drive is functioning correctly. Available spare 99%. Available spare threshold, that's when it triggers. Percentage use. This drive I just pulled from a random drive invalidation from Intel, so it's been beat up quite a bit, right? So you can see 15% used. It's probably been through dozen firmware versions, so you can see it's logged a bunch of media errors and unsafe shutdowns. So even though this drive is functioning correctly, all the media errors do get logged here if it does happen, and then that you would be able to find that. If they're not clear, they are persistent, then you'd be able to find that in the error log page. Now, if you just do a sudo nvme error log /dev/nvme 0 or whatever your NVMe device is, it'll dump the entire error log entry. And you'll see it basically, if there are errors, generally you'll have a critical warning or something in here that suggests you have errors on the drive. But if you do have an error, this is where to look to basically find out, where that error happened. Okay, and then the other things in the smart that are really interesting, and I'm going to walk through some of the temperature stuff, but you have warning temperature time, which can tell you if the drive has exceeded its thermal limit and starts to thermal throttle, critical composite temperature time, thermal management transition time. So you have all these different thermal attributes to figure out if you do have some issue where the drive overheated. Many people don't know this, but if you have an NVMe SSD that overheats, it doesn't like instantly cool down. It could take a long time to cool down sometimes, especially if there's not enough airflow. So a lot of customers, if there's some workload that ramps up a drive to a critical temperature, you'll find out right away here in the smart. Which brings us to temperature monitoring. And so one of the things you want to do on an NVMe SSD is monitor the temperature. And there are some hooks in the new version, the new kernel of Linux, to basically make this a lot easier to port over to other applications for different monitoring. Because a lot of times people just want to monitor the temperature of the drive. And this is off a drive that I knew actually overheated. And so I grabbed it in the smart log right after that happened. And basically when the drive was overheating, when it was over the critical temp, the smart log critical warning bit changed to OX2. And you can look back here in the critical warning bit, basically this bit's going to be set to 1 if a temperature is greater than or equal to an over temperature threshold or less than or equal to an under temperature threshold. So the drive was functioning correctly. It went over the critical temperature, and then the critical warning bit went off and told us that it was, and then it logged the time in minutes over here and the warning temperature time about how long it was over the temperature. So again, there's lots of stuff in the smart, but basically, if you're doing especially like large block sequential write for sustained many hours, that's going to heat up the drive. And if you have a weird failure, in this case, when this drive, in this validation test, when the drive overheated, the drive de-enumerated. It did what it was supposed to do, which was thermally shut down. Most drives actually thermally shut down when they reach the critical temperature. So in Intel's case, in this case for this drive, it was 70C, which is a composite temperature. And at 70C, it basically shut down. And it was doing what it's supposed to do, is prevent from overheating the components and damaging them. So again, if you see something like that, the temperature in smart is where to go. The other thing is, NVMe has an entire spec for management, and it's called the NVMe Management Interface Specification. So the NVMe MI is basically for a spec that allows for both in-band and out-of-band management. So out-of-band management meaning independent of the host operating system, so we're agnostic to the operating system. And today, that out-of-band management can be done through PCIe vendor-defined messages, or through most commonly SMBus or I2C down to the drive. And now the benefit of that obviously is to be able to provide more data out of band. So if things are going on in basically, a system console or management console can look at the drive and report data, smart data from the drive, without having to go through the operating system. Now, the methods I showed you before, in-band is great because you can get all the information you can ever want out of a drive. Now, the benefits from out-of-band are very clear. So my dear friend Austin Bolin from Dell, who spent a lot of time, he's one of the workgroup chairs for NVMe Management Interface, provided me some of these screenshots from Dell iDRAC. And this is iDRAC 9 Enterprise. This is something you get with a Dell server, and I know HPE has something similar with I think they call it ILOM. But basically, all these different OEMs have their management consoles that work out of band, and they use the capabilities of NVMe MI to basically monitor SSDs out of band. So you can run this through a web console independent of any operating system. It doesn't matter, the drives can report information to this web console independent of any operating system for streaming data. And you can go read all about iDRAC here, but I'm showing you guys some information you can get on SSDs. Like, here's just an example of like if a drive failed, this is what it would look like. You could monitor this out of band, and basically from a management console, without even having to go into the OS, you can click on the drive and it will say, oh, it's failed, or you can figure out if something's going on with the PCIe negotiation, if it's not linking up at the desired speed. This is a P5500, which is our Intel's new Gen 4 drive. So you can see it's linking up at Gen 4x4, which is good. But so yeah, again, this is what NVMe MI is used for. Again, here's just an example of like what it would look like if for a management console. But this is basically why NVMe MI exists. So customers like, or I guess companies and OEMs like Dell and other OEMs want to be able to support this type of debugging of drives without having to be dependent on the operating system commands. Because again, operating systems is great. They're super powerful, but every version of Linux is a little bit different. It's different capabilities in Windows, and they want to be able to do this from a combined management. So if you want to do health monitoring of NVMe SSDs outside of the operating system, go through your management console for your OEM, or if you're developing software, NVMe MI is a great choice. Okay, so let's see how I'm doing on time. 20 minutes. Okay, telemetry log page. So telemetry log page I mentioned is basically for when an SSD fails. You can read the telemetry log page. There's stuff that you can go in the spec. It's not if you're implementing this, you'll probably want to know there's host initiated and controller initiated and other kind of things in the spec. But basically, I mentioned telemetry. The most important reason for telemetry is when a device fails, somebody can run this telemetry command, dump the log, and depending on what size of the log they want, there's different data areas for how big the log could be. But basically, if a drive fails, they want to send this back to the SSD vendor or SSD developer or the OEM or whoever, and then start be able to do root cause and debug the issue. And then telemetry log, is encrypted, so and there's some of the stuff that is human readable, but depending on, it's up to the vendor. The telemetry command in NVMe just basically says, here's how to dump the data. Once you get the payload, then it's up to whoever dumps that to go send it to the SSD vendor to debug. But it's super important command in NVMe. The other one we talked about briefly was device self-test, and I mentioned if you're repurposing a drive or taking a new drive into a new system or something, and you want to just make sure everything's operating correctly, you can run the device self-test. The short test is supposed to be 2 minutes or less. Extended, it basically says in the device self-test log about how long it's supposed to take. Depends on the drive vendor, but basically this test basically just runs through this. Vendors can implement a specific device self-test that they want, or they can follow kind of the example in the NVMe specification that goes through, checks the RAM, checks the smart, checks the volatile memory, checks the metadata, NVMe integrity, data integrity, media check, drive life, the endurance, all that stuff. And so, again, if you want to know a simple operation, this is an NVMe 1.3 feature. So some of the new Gen 4 drives and some of the new NVMe 1.3 drives that are out will support this command. If you have an older NVMe drive, probably doesn't support this. But it's one of these new features in NVMe that's just kind of a nice quality of life for being able to do a short, easy test that gives a nice log if it finished, and be able to identify if the drive is working properly. The other thing is a persistent event log. And so basically, the persistent event log, as I mentioned, is kind of like the black box recorder for all the things that happen on the drive. There's to not be too confusing, but it's in NVMe 1.4, and there's some other variations and future work that are going on for technical proposals to enhance the work there. I'm not going to go through all of them, but basically, remember this just records things on the drive into when they happen, and somebody can dump this persistent event log, and it gives you a human readable log with timestamps of everything that's happened on the drive. So I get a ton of questions. I help out from being a validation background and helping out just people doing general development. I get a lot of comments on, okay, well, most of the time NVMe SSDs today are running on top of PCI Express, and so when you have an error, boy, it's tricky, right? Again, I mentioned it could be a file system, it could be your application, it could be in some cases it could be PCI Express, and being able to know some common debuggability tools are helpful to be able to identify when things are happening. So sometimes in Linux, dmessage is definitely where you want to go to basically have all information about kernel errors or driver information. And if you have PCIe bus failures or retries or advanced error reporting failures, they'll show up in dmessage. If you have if the NVMe driver can't create queues on a NVMe controller, or for some reason there's a reads failing or something, they'll show up in dmessage. The other thing you want to do is the LSPCI will give you a detailed PCIe topology. Again, sometimes you just need to know what's going on. If a device is for instance not not performing as well as it should, maybe it's not linking up at PCIe Gen 3 or Gen 4 or whatever the drive supports. Maybe it's not linking up at 4 lanes or 8 lanes or whatever the drive supports. So LSPCI is going to be able to tell you information about that. And then LSBlock, and I mean, there's millions of commands in Linux. I'll share, there's if just things like if drives are full or memory's used, like stuff like DF or DU. So disk usage, you can find out if weird things are happening. But yeah, anyways, there's a lot of stuff, more than I can talk about today. But, here's some examples of demessage, if basically, if you get a message like this, PCIe NVMe 0 PCIe function, you can kind of point back to that PCIe tree in LSPCI to figure out which device it's coming from. If you see timeouts, this is, by the way, I borrowed this slide from an old colleague, Keith Bush, who now works at WD. He gave, as one of the Linux developers for NVMe, and he's one of the original developers for NVMe CLI and Linux NVMe driver. He kind of wrote this, 999 out of 1,000 times, the controller it's messed up, not the OS. If you see some weird timeout issues, which, okay, I'll take his word for it. And then the failed initialization, you can see obviously somebody wrote initialization that was from the UK or whatever. But basically, the controller didn't acknowledge the enable sequence. So if you have some weird failed initialization where you see the PCIe device, but you don't see the NVMe device in NVMe list, then it could be something weird where the initialization sequence didn't complete. Shutdown, right? Again, this is kind of really important on big drives where it can take a long time to shut down. Basically, if drives have to dump their metadata or have large power loss capacitors, you might see something like this where the device shutdown was incomplete and aborted, and then you'll get back in the smart attributes monitor something called unsafe shutdown. So if that happens, you'll see something like an unsafe shutdown. Here actually, while making this presentation, I had a weird adapter. I used one of these M.2 to U.2 adapters for plugging in a U.2 to a desktop, and the drive was being flaky, and I figured out, oh, this is funny. There's some PCIe bus errors that are being corrected, which is funny. Yeah, so basically, I grabbed this screenshot very recently, a couple days ago, when I saw it. But you can see this is just stuff in dmessage where you can find out if things are going wrong. My favorite tool, sorry for this, this is basically some screenshots from my desktop. I like to use this weird, black screen and green text, my little hacker text for my terminal in Mac. But you can see this is basically two commands, iostat and dstat. These are my favorites for monitoring the performance. There's a million different applications you can use to monitor performance. But basically, iostat will tell you if you give it a specific device like NVMe 1 namespace 1, it will monitor the kilobytes read, kilobytes written. You can see the M. If you do the -H on the end, it'll give you human readable, so it'll give you in megabytes. And basically the TPS or the IOPS. dstat will give you the read and write aggregate for the entire system. If you see stuff like IO weight over here, then you might be getting IO bottlenecks on the drive, and you do see the IO weight start going up. Or if you see high amount of paging, you can see some DRAM issues. So anyways, iostat and dstat are super critical to understanding, if you're diagnosing a performance problem, which are a lot of problems. These are just some information I'm going to leave with you guys in the slides. I don't have time to go through them, but if you wanted to go very, very deep on NVMe, they do have kernel tracing available, so you can enable kernel tracing on the commands. Like this is the command instructions of how to enable kernel tracing for NVMe. And then if you wanted to see what that looks like, this is just a command where it's doing a DD, where it's just writing 1 megabyte in one block. And this is basically what the NVMe trace looks like of that command. So you can see the QID, the namespace ID, the command ID, blah, 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 metadata, so LBA length and size and all that stuff. So if you wanted to really go deep on debugging, you could use this. Probably not required for most people that aren't developers. The other tool that I really like that Intel has contributed to is called IO Tracer. And here's the link here on GitHub in the OpenCast. It's called the standalone Linux IO Tracer. But basically, you can run this tracer, and then you can enable this driver. And then if you run your whatever workload you want to run, you can use this tracer to basically collect the system traces, and then they have a report summary that parses the data to a CSV or JSON. And then basically you can do stuff like LBA distribution. So if you wanted to see like locality for caching, you could do that. You can look at latency histograms of all the commands on different block devices. to basically see what the average queue depth of over a real workload is. So this is super helpful. Again, if one of the things we were using this for was like debugging some stuff in a MySQL database. We weren't seeing the performance. We weren't seeing the disk utilization very high. We ran this, and then all the writes were going to the disk, but all the reads were coming from DRAM. So you could see that in the trace that no reads were coming from the drive. So this is a very useful tool. And one, it's open source. You can just download it and compile it and install it if you want to go run a very specific workload and learn more about it. The last thing I'm going to talk about, I guess I'm almost out of time for my 30 minutes, so is the OCP Cloud NVMe SSD spec. So Microsoft and Facebook have done a wonderful thing and got together and open sourced their SSD specifications into this thing called the OCP Cloud NVMe spec, and it has lots of stuff like PCI Express features, NVMe features, smart log requirements, and this is the one I'm going to talk about a lot today. Is they have some custom smart log, and it's called the C0 log page. It's called the Smart Cloud Attributes log page, and this is amazing because now NVMe was designed, remember, to be NVM agnostic. It was designed to be able to support 3D NAND or Optane or storage class memory, whatever, what have you. So a lot of the NVMe spec was written agnostic to NVM, but at the end of the day, most NVMe SSDs use NAND, and you want to learn about that NAND, especially when you're trying to debug issues. So what this smart attribute log page does is actually has an kind of open source way in a vendor's OCP log page where you can run this command and dump the log page, and it will give you all this detailed information about XOR recoveries, bad user and system blocks, physical media units written. So if you want to calculate write amp, so you'd have like host and NAND writes, ECC errors if you were to see kind of physical device things, end-to-end correction counts for the PCIe layer, all kinds of really awesome stuff is in here. And again, just by itself isn't really useful, but if you have tools to be able to basically parse this data and basically use this data to in a collection of drives at scale, like how the cloud vendors are going to use it, they can do predictive analytics and health monitoring. Again, if you see some PCIe correctable errors, that might mean, hey, there's something going on with the system topology where you need to go fix. But at the application level, you might just see higher latencies or something. You don't know. But having this extra detail information is going to be super helpful for this predictive analytics and health monitoring. And I cannot stress enough how I'm commending my dear friends at Facebook and Microsoft for open sourcing this specification, because we've been doing some of this stuff for custom firmware for years, and I can't wait to get it out to other customers. The other thing they've done is the OCP Cloud NVMe specification error recovery log page. And again, you guys can just download this spec. It's open source. And the error recovery log page I mentioned, if most SSD failures are actually just firmware, well, boy, it sure makes sense to be able to actually recover gracefully from firmware issues, or when a drive fails, for the drive to be able to identify and tell the host what's wrong with me. And this is exactly what this error recovery log page does. You have this panic reset wait time, panic reset action, device recovery action, panic ID. And so the drive, for instance, if a drive just has a firmware issue, but it fails, but it can't verify the data integrity, instead of sending a technician after that drive to replace it, you could just run this command where it formats the drive and starts over. Yes, you lose the data, but in a cloud application where you have the data backed up, or it's stored in another server, another rack, or another availability zone, it doesn't matter. You'd rather just rebuild the drive, start from scratch, instead of sending a technician out there to replace it. So, boy, this is an amazing feature. I can't wait till this is implemented across the board, on SSD, because I think it's a very powerful tool. So that's it. I'm actually over my time of 30 minutes, but boy, there's a whole lot I could have gone into on all these different methods for Linux and performance. I can't even scratch the surface, but hopefully some of the other very educated, very distinguished speakers in our track can help you kind of guide through that. So again, thanks for everything. Have a good Flash Memory Summit. Bye-bye.